this point, we're ready to start talking about projections. Here's the theorem that tells us that projection exists. I'm going to start with an inner product space V, and I'm going to take W to be any subspace as long as it's finite dimensional, so it must have a finite basis. I'm going to take any U in V, then the R, I'm going to take W in W and X in W perp. So something in W, something perpendicular to W, so that U equals W plus X. All right, perfect. So this means that if I have W here, I'm going to draw W perp as a line. I'm pretending we're in R3, but really the picture could be in any dimension. I have U and V, so V is the whole space, so I have some vector here. Then we're dividing it into two parts. One part that's in W and one part that's in W perp. All right, so W is actually the projection onto W. X, we used to call it the orthogonal component, but really in this case, since we're talking about subspaces, we could think of W as the projection on W, and X, the projection on W perp, and that works well. So let me write that here. So definition. W is called the orthogonal projection of U, U onto W, and we'll write that W is the projection on the big W of U. That's the orthogonal projection, and we'll have almost the same definition for X. X is called the orthogonal projection of U onto W perp, and we write X is the projection on W perp of U. Alright, so at this point we're told it exists. We haven't proven the theorem. The theorem will be in some way proven by the end of the section without us saying so or writing so, by just the constructions we're making. But what we'll have first is we'll have formulas for W and X as long as we have an orthogonal basis. All right, so I'll give you a formula for W and a formula for X given an orthogonal basis, and then we'll prove at the end of the section that we actually have an orthogonal basis, and so that's going to give us that these exist. All right, so here's the theorem. So I'm going to assume I have an orthogonal basis, not for V, but for W. So assume let me make sure I use the same notation. Assume that, sorry, that's part 1. Assume that V1, V2, Vk is an orthogonal basis for W. All right, then the projection on W of U. We're going to start the same way we did for projections in Rn onto a vector. So I'm going to take U V1 over length of V1 squared V1. All right? So that's our projection onto V1. And then we're going to add the projection onto V2. And so on. So it's a lot like what we had in last theorem, except that in last theorem we used a basis for U, a basis for the entire space for V, so we just got U back. But here we're chopping our basis and using only a basis for W, and we get something in W. That's the projection. All right, second, if my basis is better than orthogonal, if it's orthonormal, then all of these lengths are 1, so I get something nicer. So assume V1, Vk is an orthonormal basis for W, then projection onto WU would be, well, you don't need the denominator, so I'm only using the dot product, not the norms anymore, and this is what I get. All right, so now we have a formula for projections, assuming we have a basis. So in the next few examples, I'll give you a basis, and then we'll see how to build one later this section.